we're going to go ahead and get started. So first thing, I think your first assignment on Top Hat was due sort of now. So all the questions, other than the last one, you'll automatically get a mark for, right? You've probably already seen it. The last one, like one of the TAs has to mark. So you shouldn't see a mark right now. It'll say 0, but you probably didn't get 0. Wait till one of us posts something on my courses saying, like, the assignment's been marked. Then go back and look at your marks, and then if you're not happy, come and see us, or whoever. Is that okay? Everyone's okay with that? Perfect. Okay, so last class we sort of talked about sort of weather prediction models, and so here today we're going to take a little bit of a different spin. We're going to go more into sort of like the physics of what's happening in the atmosphere. So if at any point you don't understand what I'm saying or whatever, please stop me. I'll try and explain again. Chances are if you're not understanding, someone else isn't understanding as well. And this is a bit of a harder concept than the weather models that we were sort of looking at the other day. So basically we're going to go into forces and force balances. So this basically describes why we have wind and why it's moving and why it moves in the direction that it moves in. Right? So to begin, like what exactly is a force? Right? So a force is something that accelerates a mass, right? Either accelerating by changing its speed or by changing its direction. So when I talk about a force, right, we have all different forces sort of around us, but it's really the inequality of forces that causes the motion of anything, right? So clearly we have the force of gravity on us right now, but we're not moving, right? We're not accelerating, right? So what's happening is because there's the ground underneath us, that's pushing in the opposite direction as gravity, so we're staying sort of stable. We're not moving, right? So there's no inequality of forces happening. But if somehow the floor under us got removed, we would then fall, right? We now have an inequality of forces. The force of gravity is stronger than nothing below us, so we fall down, right? So it's when we're talking about forces and acceleration, it's not just one force we're looking at. We really want to see the inequality of the forces that are acting on a parcel or an object or what have you, to see if it's moving, if it's changing directions, or if it's accelerating. Right, so a good example here is the force of gravity, right? We all sort of feel that. That's sort of what keeps us on the planet, and the planet pushing back is what keeps us from sort of flying off into space. So those two forces are keeping us sort of stationary on the Earth sort of every day. So there's sort of two types of forces that we talk about, right? There's something called a fundamental force, and there's something called an apparent force. So a fundamental force is a force that happens no matter what frame of reference we're in. So it doesn't matter if the object's moving, not moving, these forces are going to happen no matter what, right? So a good example is gravity. Even if the Earth wasn't spinning, we would still have gravity, right? The force of gravity would still exist, right? Friction is another fundamental force. No matter what frame of reference we're in, we are still going to have friction, right? So you've got sort of the forces that no matter where you are, they're going to occur. But then there's these things called apparent forces or like fictitious forces. And they arise from the fact that if your frame of reference is moving or changing directions, then you're going to have other forces sort of acting on different parts of it. So we're on the Earth, right? And the Earth is spinning. So because the Earth is spinning, we have these additional forces that we have to take into account when we're looking at sort of like changes of wind and wind direction and why we have wind. Right? So we'll get into that a little bit more, but really the important thing here is that there's two different types of forces. Fundamental, they're always going to be there, doesn't matter where you are, right? We're always going to have gravity, we're always going to have friction, and then apparent. And then the apparent forces, really they depend on your frame of reference. So if you're moving, if you're in a frame of reference that's moving, like if you're on a train moving somewhere, that's going to be different from just sort of standing still, not moving somewhere. We'll get into that a little bit more. I don't know if you guys have seen all like forces before, but if, like I said, if I'm confusing you, please stop me. We can chat about it. So a good example of an apparent force, right, is sort of a bike going around a loop, or when you're on a roller coaster, right? If the apparent forces didn't exist, when you sort of do a loop in a roller coaster, you would fall off. Right at the top, gravity would push down, and you would fall down and probably not survive. But clearly that doesn't happen, right? We all make it out of roller coasters. So what's happening here, right? Let me just get this. So as this bike is coming down the plane here, right? It's got a force. Because it's moving, it's got sort of this inertia that it's going with it, right? So it wants to keep going, right? Inertia sort of wants to keep going in the same direction unless something stops it. So it's going in this direction. It wants to keep going here, right? It wants to keep going straight. But as it hits this loop, right, it's now putting sort of another force at every point on the outside of the loop pointing outwards, right? Because it wants to keep going straight, but this loop is sort of forcing it to keep going round. So what happens is, when you have at the top here, instead of him falling down because of gravity, it's now got a force that sort of wants it to sort of go outwards, right? It's inertia force that is occurring because it's moving, because the motorcycle is actually moving. It has this extra force, but then it also has gravity that's pulling down. So if this motorcycle can overcome, if its inertia force is stronger than the force of gravity, it'll make it all the way around the loop, right? So if it's going fast enough, it'll make its way around. But if for some reason it's not going fast enough and the gravitational force is stronger, then it's going to fall down. Does that make a bit of sense? We've all seen sort of a motorcycle go around a loop, maybe? Or you've been on a roller coaster? Does that idea sort of make a little bit of sense? Okay. If it doesn't, we'll talk about it later a bit more. So that's an apparent force. So the motorcycle's not moving. It doesn't have this inertia force. All it has acting on it is gravity. So it's only going to have the fundamental force of gravity acting on it, and it's not going to move. And it wouldn't make its way around the loop. Okay. So we've sort of talked about fundamental forces and apparent forces, but sort of what are the forces that are actually acting on the air around us, right? On the wind and all that stuff. So we have three fundamental forces, right? We have the pressure gradient force, gravitational force, and a frictional force. Those are all fundamental. And the apparent one is this one called the Coriolis force. You may have heard it before if you've ever taken any type of, weather class or environment class. So we'll get into that a little bit later. But for now, these are sort of the four important forces that are acting on our air to make winds, to determine sort of what direction the winds are going in. So now we can sort of break these down just a little bit. So, okay, the pressure gradient force, right? This is a force that basically, so the world, or like the Earth wants everything to have an equal amount of mass sort of everywhere, right? If it was in perfect equilibrium, we wouldn't really have winds. But what ends up happening is in some areas we have sort of a larger amount of stuff, in this case of air. So here we have a larger density of air molecules than on another side where we have sort of a smaller amount, right? So if we have a lower pressure on one side, so this would be over here, this would be like your low pressure, and then like a higher pressure on this side, if we now remove this sort of thing that's separating them, the air molecules from the high are going to want to move to the low, right? This box wants to have the same amount of air molecules sort of evenly distributed. It doesn't want to have the left-hand side having more and the right-hand side having less. So the pressure gradient force moves air from high pressures to low pressures. I think that's sort of pretty intuitive, right? So if you think about a similar system of like water in a tank, right? If you have a tank of water and you have sort of a lot of water on one side and then sort of a divider and a little bit of water on the other side, if I now remove this divider, you're going to have water sort of slosh to the lower side to make it equal, right? That sort of makes a little bit of sense. So the point of this force, move air from high to low. That's what this force does. And this is a fundamental force. So this doesn't matter what reference frame I'm talking about, whether we're on the Earth spinning, whether we're on the moon, whether we're somewhere that's not spinning at all. This is going to happen. Fine. So the difference in air pressure that we see in different places is usually due to two different things. So either we can have a difference in air density, or we can have a difference in air temperature. So if the air density, so when I say like higher air density, there's more molecules, and the lower air density, there's less molecules. If for some reason we have an area with more molecules and less molecules, it's going to want to sort of mix together to make the same amount of molecules everywhere. So that's sort of how the pressure gradient force sort of works. So if the only thing we had on the planet was the pressure gradient force, this is sort of how it would look, right? So we have a high pressure. So these numbers here are pressure. So this is going to be like 1,020 millibars, 1,016, 1,012. So if all we have is the pressure gradient force, we're going to have a high pressure on the left here, a low pressure on the right. The winds are going to want to move from high to low, right? So they're going to want to move, in this case, if we think about like that way being eastward, the winds would move eastward. And the speed of the wind is determined by the strength of the difference of our pressures, right? So if we have a higher high pressure in the same distance as and a lower low pressure, then the winds to move it are going to be stronger, right? So more wind is going to want to move the more the molecules. So in this case, with the same distance, right? Same distance here and here, but the difference here is larger versus the distance here. So we're going to have a stronger wind going sort of eastward to try and move from the molecules from high to low. Yeah? So that's sort of the pressure gradient force in a nutshell, right? So this is only, we're talking about horizontal right now. This is sort of just another example. It's animated really well, moves from high to low. It's a great animation. Right, so a good example of sort of changes in pressure gradient and the induced winds, if you sort of think about a hurricane, right? So here's Hurricane Andrew, which hit in, I think 1992. If you look here on the right, these are the pressures that occurred as it hit Florida, as it hit the east coast of Florida. So this was a Category 5 storm that hit Florida. And the difference here, we have 1.9 millibars per kilometer. So each kilometer that we go, there's a difference of 1.9 kilometers that's occurring from this hurricane. So this type of pressure change over a kilometer gives rise to about a 45 meter per second wind. Right, so just that change in pressure over that little distance is creating those crazy winds that we see when sort of a hurricane hits land. Right, in this case, this is an extreme example. This was a Category 5 hitting Florida, so this is sort of the best example to give in this case. Right, so pressure gradient force can create really, really strong winds. And this is just another example. I think I showed this last time as well. This is the superstorm in 1993 that sort of gave precipitation sort of all along the East Coast. So if we sort of look at a similar thing, here I think we have, here the difference, so before it was about 2 millibars per kilometer, and here we have about 0.1 millibar per kilometer, right? So it's still a lot. I mean, it's not hurricane strength, but it's still quite a big difference, and that gave rise to about sort of 15 to 20 meter per second winds. So really you can see that the pressure gradient force sort of causes the difference. The stronger the pressure gradient force, the stronger that we're going to see our winds become. Yeah, okay, so here we've just talked about sort of in the horizontal direction, right? All the maps that I'm showing you are sort of X, Y. But if we think about the vertical for a few seconds, right? If you sort of go to Toronto and get on the bottom floor of the CN Tower and go all the way to the top, which is about here, I think, 345 meters, we have a pressure difference of 41.5 millibars. Right, so that's clearly big. That's bigger than sort of the values that we were showing before. So why do we not have these incredibly strong winds in the vertical direction? Right, I just said that horizontal pressure gradient forces causes really strong horizontal winds, but stronger changes are happening in the vertical, but we don't see these crazy vertical winds, right? In everyday weather, there's not crazy winds when we walk outside sort of flying us upwards or whatever. So what exactly is going on? So why don't we sort of see a similar thing happening in the vertical? So the reason that we don't sort of see these crazy vertical winds is that gravity is sort of acting against it, right? So in the horizontal, we don't really have anything to balance the fact that we have our pressure gradient force, but in the vertical, we have gravity. So the huge changes that we see in pressure when we move up, just sort of like a slight amount, is to a great extent balanced by gravity. So the balance between vertical pressure gradient force and gravity is on the order of it's like 99% in balance, right? So that's why we don't tend to see these huge sort of vertical winds. We see winds on the order of about 1 to 2 centimeters per second, which isn't very strong. Whereas for a similar pressure gradient in the horizontal, we'd get something on the order of 10 meters per second, right? So really the important thing in the vertical, the gravity sort of balances it so that we don't have these crazy winds. In general, right? We're talking about general weather here. So yeah, that's important to sort of distinguish between the pressure gradient force in the horizontal and the pressure gradient force in the vertical, because they're two sort of different entities almost. It's the same idea, but sort of two different entities. Okay, so that's sort of the pressure gradient force in a nutshell. Is that okay? Does everyone sort of understand that? Okay, well, I'll find out in the assignment if you do or don't. So the next thing, right, is friction. I think this is, everyone pretty much has an idea what friction is, right? This is another fundamental force. No matter where you are, you're going to have friction. So basically, friction works opposite to the direction of movement, right? So no matter what way I push, like if I push a box along this floor, the friction's always going to be pointing behind me. It always sort of makes it harder for me to move something. And the same thing is true with air. So whatever direction the air is going, friction's always going to be sort of pulling against it, right? And depending on what surface we're looking at, right? So if I push a box here, or if I push a box along ice, the difference in force that I have to apply is different, right? So this floor is sort of a bit rougher, so I'm going to have to push a little bit harder to get the same acceleration than along ice, right? So important thing, they're always sort of working against each other, and that this guy's a fundamental force. So sort of what's happening sort of in the atmosphere. So we have different types of friction. The first one here at the top is probably pretty intuitive, like clear. You have a whole bunch of buildings, so when air is flying over them, like the air that's close to the surface is going to be affected by the fact that, you know, a building is rough, right? Like if you rub against it, it's sort of rough. It's not as smooth as, say, just like clean air. So you're going to have sort of friction that's produced by buildings, by the ground, by trees, by whatever's around you, right? We have sort of another one that's sort of like thermal friction. So once we have sort of like an air parcel that's rising for some reason, it's sort of lighter than the air around it, so it starts to rise. As it's going through the air, it's sort of experiencing friction from the air around it. It's not a lot. We're not talking about a lot of friction, the air-on-air friction, but it's still non-negligible. Like we still need to think about it from time to time. And then the last one here, if you just sort of have two different speeds of wind, so if we have a strong wind and a not so strong wind, we're going to create some friction sort of between this. So the slow wind is going to sort of slow down the faster wind if they're sort of close to each other. So really the idea of, well, I think it's next. Yeah, so the idea of friction, it's just works against whatever direction we're trying to move something. And it's really, it's most important near the ground. Once we kind of get away from the ground, away from trees, away from buildings, friction, we don't really care so much about it. So it's really when we're talking about friction force, we're talking about the lowest 1 to 2 kilometers. Above that, we don't really mind so much. Okay, so the Coriolis force. So this one's probably going to be the most confusing, and I'm going to do my best to explain it. And at the end, I'm just going to tell you to memorize something if you didn't understand it. So just let me know. So basically, this is the apparent force that I was trying to sort of talk about at the beginning. The reason that we have the Coriolis force on Earth is because we're spinning, right? The Earth is spinning. So we are in a reference frame. When I say reference frame, sort of like what we live on, right? Our reference frame is always turning. We don't feel it because it's turning really slowly, but it's still happening, right? So because we're on a system that's rotating, we now have this extra force that we need to sort of take into account. So if the Earth wasn't moving, the Earth was just stationary, this force wouldn't be there. This force is there because we're turning. So you can sort of, I guess the best sort of example to compare it to is if you're on like a merry-go-round. You probably haven't been on a merry-go-round in 25 years, but or 20, I don't know how old you are, whatever. So if you're at the center, right, of the merry-go-round, it's spinning at the same speed, right? The edge of the merry-go-round isn't spinning faster than the middle. The whole thing sort of moves as an entity. But if you're sitting on the merry-go-round, right, if you're at the center, you're sort of spinning slower, like your speed is slower than the person at the edge of the merry-go-round. So for the same distance, right, so for the same speed that this thing is turning, someone on the edge here, at the edge of this merry-go-round, sort of this person here, has to be moving faster to keep up with the person in the middle, right? Because it's all moving together. If you guys were moving at the same speed, this person wouldn't be on this. This person would sort of be moving backwards. Is that, maybe? Okay. So the idea, I don't know if this is can I do this? No, how's that? Get rid of this pen. Oh, that's not what I wanted. Let's take a look. Let me see if we can get this to work.
In this view of Earth from space, it is clear that the Earth is rotating. However, as an observer on the surface of the Earth, the only indication our planet is rotating is in the observation of the sun during the day and the stars during the night. Every day the sun rises in the east and sets in the west, but we are completely unaware that we are traveling to the east at hundreds of miles per hour. So just how fast are we moving? Well, at the equator, the rotational velocity of the Earth is an incredibly fast 1,018 miles an hour. If you were to travel from the equator to about 30 degrees north latitude, the rotational velocity would have slowed considerably to about 882 miles an hour.
Right, so that's sort of the same idea as the merry-go-round, right? So because the Earth is moving as sort of one entity, right? So the equator and the North Pole, they're spinning, like they're spinning together, right? It's not, one's not spinning sort of quicker than the other one. But the fact that we're a sphere, that the person, like, so because we're sort of like a round sphere, the person sort of at the equator to sort of go the same rotational velocity has to go faster to sort of make up the fact that he has a bigger distance to go, right? So the person here, if we're rotating like this, has to sort of go faster around. You can sort of think about it like, you know, when runners sort of around a track, when they're doing the long distance run, right? So the ones in the middle aren't running as fast, right? They don't have as far to go, but the ones on the outside do. That's where they sort of switch. It's the same kind of idea here. Someone at the equator has a longer distance to go, so they have to be going faster to be at the same location, sort of the same, like, vertical location. Let's just keep going and see if that makes sense.
Well, why? Well, as you walk north or south from the equator, you're actually getting closer and closer to the Earth's axis of rotation. Because the surface of the Earth is solid, the rotational velocity will decrease as you walk north or south from the equator, because you're actually getting closer and closer to the Earth's axis of rotation. To understand this better, let's imagine that we take the Earth, a sphere, and flatten it out into a rotating disk, like a merry-go-round. If you were to stand on the edge of the merry-go-round, the rotational velocity would be large, and you would feel like you're going to fly off. However, if you stand in the middle, the rotational velocity would be much less, and you would feel like you're barely spinning at all. Now, what if we were to have two people sit on opposite sides of the merry-go-round and try to throw a ball to one another? You can see that as the ball leaves the hands of the person throwing it, it becomes independent of the rotation of the merry-go-round, and therefore follows a straight path. But because the person trying to catch the ball is still rotating with the merry-go-round, they are quickly moved out of the ball's intended path. Because the merry-go-round is spinning counterclockwise, this deflection is to the right. If it were spinning clockwise, the deflection would be to the left. Now, to an observer above the merry-go-round, the path of the ball appears straight. However, to people on the merry-go-round, the path of the ball curves to the right of the intended motion. This experiment demonstrates how the rotation of the merry-go-round appears to cause a deflection in the path of the ball. This also demonstrates how air movement on the Earth's surface can be deflected by the Earth's rotation, a phenomenon called the Coriolis effect. How do we relate the effects of the Coriolis force to air motion in our atmosphere? To answer this question, let's first investigate what would happen to a parcel of air that was initially at rest with respect to the Earth. At 30 degrees north latitude, the parcel is traveling to the east with the Earth. But if we were to shove this parcel at 10 miles an hour to the north, what would happen to its motion? We have already seen from the merry-go-round experiment that the ball would be deflected to the right. But why? The answer lies in understanding something called the conservation of angular momentum.
Okay, I don't really want you to think about this for 2 seconds. So let's just go back. Let's see if that, oh no, let's just get it here. Right, so, okay. Is there a picture of... Right, so sort of the idea is that because someone at the equator is sort of moving eastward faster than someone, say, in Montreal, if they were trying to throw a ball, they were super duper strong and can throw a ball from the equator to Montreal, when they throw it, the eastward component of that ball is bigger than what we have at Montreal. Right, so because they're moving fastward eastward, their ball is also moving eastward, so when they throw it, it's actually going to deflect to the right, from what we see. Right? The ball's actually going straight, but because we're on a rotating planet, it looks like the ball is getting deflected to the right, just because their eastward component is faster, because they're rotating sort of their tangential sort of component is faster than we are in Montreal. Sort of? Maybe not. Okay, we'll try again. Let's not do about that one. No, it's okay too. So, okay. So here we've talked about sort of that if I throw a ball, like the Coriolis effect sort of affects it if it's moving north-south, right? The component's going to be, it's going to deflect to the right. But the component is not only in one direction. So if we think about, sort of this would be like a vector sort of moving, like winds moving east-west, so along sort of like a latitude circle. There's a component both sort of to the south and also vertically upwards to this vector, right? So here it's sort of pointing outwards, but if we were going to break that vector down, there would be a north-south component, right? So this is north, this would be west, I guess. The wind is sort of going west, so from east to west. We would have a component vertically, so this is like our z direction, and then this is our north-south direction. So the Coriolis effect isn't just in one direction, it's component form, right? So we're going to have a component both in the vertical and in the north-south direction. So basically, the whole point of this is just to say that in the northern hemisphere, winds get deflected to the right by this effect. So wherever you are in the northern hemisphere, if you have winds, they're going to get deflected to the right because of this. And if you're in the southern hemisphere, they're going to get deflected to the left. So that's sort of the important sort of part of it. So there is a vertical component to the Coriolis effect, but it's so much smaller, it's orders of magnitude smaller, that we kind of just ignore it. So really the important part when we're talking about different balances is going to be in the horizontal direction. So I think, right, so if anything, like the physical explanation I tried to give made no sense, and that's very, very possible, really just the take-home message, and this is really, really important, you need to just memorize this or whatever, is that it gets deflected to the right in the northern hemisphere. So if you have winds moving, they're going to get deflected to the right. And the important thing, which I don't think I really talked about all that much, is that the strength of the Coriolis force is related to the strength of the winds. So if you have no winds, so if nothing's moving, the Coriolis force isn't doing anything, doesn't exist. Right? You have to have something moving in a direction for the Coriolis effect to kick in. And the stronger they're moving, so the stronger the winds are moving or the stronger an object is moving, the stronger the Coriolis effect is going to be. So the Coriolis effect deflects to the right in the northern hemisphere, to the left in the southern hemisphere, and is dependent on the strength of the winds. That's sort of the important part of everything that I just said. So just try and remember that if you can. And if you want a better explanation or you don't understand, we can talk about it after. Okay, so that's the Coriolis force. So that's the apparent force that happens because we're in a system that's rotating. Because the Earth is actually rotating, we have this extra force that kicks in. Okay, so that's sort of all the forces that we're going to sort of talk about that are important for winds. But really, so the important thing that I think I talked about a little bit before is to get an acceleration, so that means like winds are speeding up or slowing down, for anything to speed up or slow down, or to change direction, what we really need is an inequality of forces, right? You can have forces acting on something, but if everything's perfectly balanced, we're not going to have an acceleration. So a good example of this is sort of if you think about flying in a plane, right? So when you're sort of cruising at a constant altitude, you're not changing directions, and you're not changing speeds, then everything is in balance, right? So if we're talking just in the horizontal, your drag force, oopsie daisy, there we are. So like your drag force is going to be equal to your thrust force. If you want to speed up, now we need to increase the thrust force so that we're accelerating in the forward direction. And same thing for if we're sort of cruising at a constant altitude, sort of in the vertical direction. If our weight, sort of the vertical, the gravitational force needs to equal our lift force. If those don't equal each other, if one is stronger than the other one, now we're going to start to see the plane move up or down. But when we're cruising, hopefully it's not moving up and down, and those two things are equal to each other. So it's the important thing is really the inequality of forces, not so much the actual forces that are acting on it, sort of when we're talking about acceleration. Okay, so here we're just going to get into some of the balances that we see in the atmosphere. So when we're talking about sort of horizontal motions above the boundary layer, so when I say boundary layer, that's sort of the friction layer that we talked about. So that's, above 1 to 2 kilometers. And the point of saying that is now we're just going to ignore friction. Above about 1 to 2 kilometers, we don't really need to worry about friction so much anymore. It's not really going to play that much of a role. So the acceleration that we see from the horizontal motion above the boundary layer is basically just a balance between, is a combination of a horizontal pressure gradient force, the thing that moves air from high pressure to low pressure, and this Coriolis force, so the thing that we just talked about that deflects the winds to the right in the northern hemisphere. So if those two, if the horizontal pressure gradient force and Coriolis aren't in balance, we're going to see an acceleration. So those are the two sort of important ones when we're talking above our boundary layer. If we now decide to start looking inside of our boundary layer, it's the same idea. So we've got a horizontal pressure gradient, the Coriolis force, except now in this case we have friction, right? So we're sort of in the lower part of the atmosphere. Things like trees, buildings, all that we're going to have to start caring about because they're going to start changing the direction and speed of our wind a little bit. And then in the vertical motion, that's a little bit easier. That's really just between the vertical pressure gradient force and gravity. So like I said before, those two tend to balance each other out really, really well to almost sort of like a 99% accuracy. So those tend to be okay. We don't tend to see that many accelerations in the vertical. Okay, so as I just said, sort of the vertical pressure gradient and gravity sort of balance each other out well. So we have a name for that. And the name for that is called hydrostatic balance. So when I say something is in hydrostatic balance, that means that the vertical pressure gradient force, so the thing moving stuff from high to low, and gravity, the gravitational force, have balanced each other out perfectly, and we have no acceleration. So if we have no acceleration, we have no vertical winds. So literally these two guys, there's an equal component going up and an equal component going down, so nothing's moving in the vertical. Right? So that's sort of what we tend to see most of the time. Sort of when there's really like boring weather, sort of sunny and nice, that's sort of what's happening. We don't really have much going on. So that's hydrostatic balance. So that's just a good word to remember. If we just say in an exam or whatever, it's in hydrostatic balance, we expect you to know that. We expect you to know that that's the balance that we're talking about. So that's sort of what's happening in the vertical. And so the horizontal is a little bit different, right? So what we have here is sort of just like a cross section. So north pointing in this direction, east is over here. And then these are just sort of different pressure levels, right? So we're talking horizontal now. Forget the vertical for a few seconds. So what ends up happening in the horizontal is we start off with some type of pressure difference because of temperature, because of air density, what have you. We end up with sort of a higher pressure somewhere and a lower pressure somewhere. So if we have a difference in pressure, now this is going to create our pressure gradient force, right? That was that force that wants, to move stuff from high pressure to low pressure. So we see the winds kick in. So right away, we have this point. So we're going to move. We're going to move from left to right, sort of on this plot. This is sort of like how the winds would adjust to the fact that there's a difference in pressure. So right away, the winds are just going to want to move from high to low. So they start moving, right? They started at rest. Now they're moving. So they're going from this high pressure of 500 millibars up to this lower pressure of 495 millibars. So we've got sort of a wind sort of going in that direction. But because we're on a rotating planet, the second we start the winds going, the second we start something moving, now the Coriolis effect is going to kick in. So the Coriolis effect always works to the right, and it's always 90 degrees to the right. So here we have sort of our pressure gradient force pointing that way. The winds then are also going in that direction. But now we're going to have a component of the Coriolis force that's pointing perpendicular, so to the right of the direction of the wind. So we have, instead of the winds now being vertically upwards, they're now going to sort of be slightly tilted by the fact that we have a Coriolis vector sort of going in that direction, pressure gradient force going in that direction. You're going to have your wind sort of going in the middle, right? So we have our winds sort of starting to slowly increase. And as they increase, as the winds start to increase because of the pressure gradient force, the Coriolis force also increases, right? So you have this increase in your wind, which causes an increase of your Coriolis. Your pressure gradient doesn't change, right? That's just created by the fact that you have sort of a high over here and a low over here. That's going to stay the same no matter what the speed of your winds are. It's the Coriolis that changes dependent on your actual winds. So we start seeing an increase in your winds. The increase in winds causes an increase in your Coriolis, blah, 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 until you reach a point where the Coriolis force sort of pointing in one direction and your pressure gradient force pointing in the other direction perfectly balance each other. So right in this case over here, we now have the Coriolis force pointing like to the right, so pointing, I guess, south. Your pressure gradient force pointing north to the left, and they're perfectly balancing each other. So the wind is happy. It's good. It's got equal forces happening on it. They're balanced. So now you're just going to keep this wind at a constant speed, moving along sort of like a constant isobar. So this type of balance is called geostrophic balance. So it's really the balance between your Coriolis effect and your pressure gradient force. And once those are in balance, we have no more acceleration. The winds are just going to keep going at a constant speed since they're equal. They're in equal balance. So a good example of this is sort of here we have an upper level map. So this is a 500 millibar level. So we're sort of higher up in the atmosphere. So we're forgetting any things to do with friction. And these sort of white lines here are height contours. And what happens is your winds, because you're generally in geostrophic balance once you're sort of higher up in the atmosphere. About sort of 95% of the time we're actually in this balance. So the winds are just going to be sort of following along these lines pretty closely. So once we give you sort of a wind map, you guys can actually figure out a lot of stuff from it, right? So if you know that the winds are going to the east, right, and we know that the Coriolis effect is always to the right in the northern hemisphere and the pressure gradient force is always to the left, from this map you could figure out that we have a low pressure sort of up there and a high pressure down there, right? Like I've given you nothing about where the pressure, what the different pressures are, but just by the fact that if I give you the winds at an upper level, you can figure out, or you should be able to figure out, sort of a general idea of what the pressure looks like. Right? Does that make a little bit of sense? That from winds, literally just from the winds, you can figure out what the pressure field looks like. Because you know that sort of in the northern hemisphere, if I have winds going that way, and they're in geostrophic balance, which they tend to be in the upper atmosphere, sort of pointing left is going to be your pressure gradient force, pointing right is going to be your Coriolis force, and if they're balanced, then you know that your low is going to be north, and your high is going to be to the south. Yes? Maybe we'll go over that again. Right, yeah, so here, same idea. This is just even higher up in the atmosphere, so now we're looking at sort of like a jet stream, and we have a 300 millibar pressure level surface, and these are our heights again. And so these are the winds that we have here, and sort of same idea, right? If they're in geostrophic balance, which they tend to be, then you're going to have sort of a low in this general region and a high in this general region. Since the winds are going from west to east, pressure gradient force points sort of to the left, our Coriolis effect to the right. That gives us our low sort of up here and our high up here. And in addition to that, because we're talking about the upper atmosphere, you can also infer something about the temperatures. Right? So higher up in the atmosphere, pressure levels, so a low or a high, are directly related to temperature. So if I ask you sort of where's the cold weather, or like where's the cold temperatures and where's the warm temperatures, you should also be able to figure it out from if I just give you the winds. So just giving you the winds tells you that sort of we have a low up here and a high down here, and because we're looking at the upper level, lows are related to cold temperatures and highs are related to warm temperatures. Right? Only in the upper atmosphere is that true, though. That's not true at the surface. But because we're looking at higher up maps, this is true. So just giving a map of winds can actually give a lot of information, just because of this geostrophic balance that we're talking about. So if we say geostrophic balance, we expect you to know that that's sort of the balance between this pressure gradient force and the Coriolis force. Okay, so as we move up in the atmosphere, the winds tend to get stronger, right? As you saw sort of here, this is at 300 millibars, so that's really high up in the atmosphere, and we have really, really strong winds, right? So why does this happen? Like, why do we see an increase in strength of our winds as we move up? Since it's just, we're talking still about a balance. So the reason for that is if we think sort of like this is the south and sort of this is the north, right? In a warm area, as you move up in the atmosphere, right, the pressure levels sort of separate more and more and more and more. Whereas compared to sort of in a cold place, those pressure surfaces are going to be sort of more packed together. Right? So you can see sort of as you move up here, the slopes of these lines tend to become steeper and steeper and steeper and steeper. Right? So these lines just being constant levels of pressure, And this is our heights going up that way, just to make sure. Right, so as we move up higher in the atmosphere for a warm location, the pressure surfaces separate more and more and more and more, and in a cold location, they squish together more and more and more and more, right? So as we start moving up, this is now causing a larger pressure gradient force, right? So if we said that temperatures are directly related to highs and lows, if we have sort of warmer temperatures here, this is going to be sort of like a bigger high, and this is going to be like a lower low. So if we have a bigger change in pressure over a given area, then we're going to have stronger winds, right? So as you can see here, sort of as you start moving up, further up in the atmosphere, we have a larger pressure gradient force. So if we have a larger pressure gradient force, we're going to have stronger winds. If we're going to have stronger winds, this is now going to cause the Coriolis effect to be bigger, right? So just as we move up, we're going to have stronger winds because of the fact that sort of our slanting in pressure is sort of bigger and bigger and bigger. So we have sort of a bigger difference in pressure the more we move up compared to the south compared to the north, especially sort of in the winter. So this is just a similar example, right? So our 500 millibar surface, if in a warmer area, is going to sort of slope downwards as you move to a colder place. So if we're in Barbados compared to here or whatever, this surface is going to slope sort of downwards as we move more to a colder place. So that relationship's only true, though, for the upper atmosphere. Don't tell me in a test at the surface that temperatures are equal to pressure, because that's not true. Don't tell me that. Okay, so this is probably just a good example. So the jet stream tends to move sort of it's stronger in the upper atmosphere because of the fact that our pressure gradient force is stronger, and it tends to move sort of like from the west to the east. So this is sort of the reason that when you're flying, so if you're flying to Vancouver or flying back from Vancouver, the flight times aren't the same, right? So the reason for this is basically because of this jet stream, because of the really strong winds due to the fact that our pressure gradient force is stronger higher up than lower in the atmosphere. And it's quite a significant difference if you've ever sort of flown to Vancouver or flown back or flown to Europe and flown back. So the reason for that is when you're flying sort of to Vancouver, you're flying against the jet stream, right? So the jet stream is going from west to east. So you're flying at a slower speed, right? You're going sort of about 640 kilometers an hour. Whereas when you're coming back, you sort of have this tailwind that's sort of helping you push along. And that is completely because of the jet stream. So when planes fly, they try and fly sort of at the level of the jet stream to take advantage of that when we're sort of coming back. So that's just sort of a reason why there's a huge difference when you're sort of flying there and flying back. Okay, so we've talked about geostrophic balance a little bit. When is it applicable? It's applicable above the boundary layer, so the friction layer there, which we said was about 1.5, 2 kilometers-ish. So what happens at the surface, right? So now we've got friction going on. That's going to change, that's sort of going to change things a little bit. It's going to change the balance that we're talking about. So at the surface, we now have to take into account friction. So basically what's happening, if we had no friction, right, we would be in perfect geostrophic balance. We'd be following the isobars. It would be good. But so what friction does, sort of what we said before, it always works in the opposite direction of whatever the movement is. So if the wind is going in that direction, the friction always wants to work backwards. So it always wants to slow it down. So if we're slowing down the wind, so let's just take this geostrophic balance for a second. So friction's pointing in that direction, right? That's going to slow down the winds. So if we're slowing down the winds, that doesn't affect the pressure gradient force, right? The pressure gradient force is literally just due to the fact that you have a high and you have a low, and the wind wants to move from there to there. So the friction doesn't change that at all. What the friction does change, though, it changes the wind speed. So if it's working against the wind, it's going to slow it down a little bit. And if we're slowing down this wind a little bit, that's then going to change your Coriolis force. Right? Your Coriolis force is directly related to the speed of your winds. So if your winds are slower, your Coriolis force has to be weaker. There's no choice. So now we're going to have sort of an imbalance of forces. So we have a pressure gradient force up here, which hasn't changed, because our highs and our lows are still the same sort of magnitude. But now that we have a weaker geostrophic wind, we're now going to reduce this guy here. So instead of it being sort of this long, it's going to be kind of like, it's going to be a little bit shorter. Right? So now we have an imbalance of forces. We have a stronger force sort of pointing to the left, sort of up here, and a weaker force pointing to the bottom. So that's going to cause the winds to move. Right? If you have a stronger force pointing in one direction, the direction of the resultant vector is going to be in that direction, right? So you have sort of a stronger pressure gradient force than Coriolis force, which then causes your winds to sort of shift a little bit. And the winds are always going to shift in the direction of your pressure gradient force since that's the stronger vector, right? That's the bigger one. So what ends up happening is your winds sort of flow into your low pressure system and flow out of your high pressure system. Right, so if we were in perfect geostrophic balance here, so friction wasn't an issue, the winds would literally just be going around in a circle here, right? They'd be going this direction. But because we have friction that's kicking in, now we're going to have the pressure gradient force is stronger than the Coriolis force. So the winds are going to sort of slightly shift inwards towards the low, and if we're talking about a high, they're going to shift outwards toward the high. They basically always want to go in the direction of wherever the low is. So friction causes winds to spin in over here and sort of spin out over here, right? And we're only talking about the lowest sort of 1 to 2 kilometers here. Above that, friction doesn't really do much because there's not really, it's really like we're talking about like buildings and trees and all that sort of stuff that affects sort of the wind direction here. Is that understood? So friction, lowest 2 kilometers makes it spin into a low, spin out of a high. And that's just because our pressure gradient force isn't actually changing. So that stays the same, but because our winds are going slower, then everything else sort of, the Coriolis effect, smaller. Okay. Okay, so here's just sort of another example. If we have, so what friction can actually do is if we already have a high or already have, well, like let's talk about the low for a second. If you already have a low, you're now going to have winds sort of spinning in towards it. Right, so instead of following the isobars perfectly, they're going to sort of spin in towards it, and they're going to converge at the center. So if we have winds converging at a location, right, it can't go through the ground. It has to go somewhere. It can't just sort of build up in the middle and then just disappear. It has to go somewhere. It can't go through the ground, right? That's pretty tough to sort of drill through with air. So it's going to end up going up. It's going to end up rising. So if we have sort of air rising, sort of in a low pressure system, that's what we sort of creates like our clouds and everything. So that's sort of, yeah. And then in the other sort of idea, if we have winds spinning out of an area, right, you can't just leave a void of air somewhere. Something has to be filling whatever was there. So in a high pressure system, we actually have winds sort of coming down from the upper atmosphere to fill that hole where the winds are spinning out because of friction. Okay, so here's just sort of a summary of all the things that I think we just talked about. I don't really feel like reading that to you guys. I think I talked about it a lot, but it just gives you sort of a general idea of everything that we talked about, the hydrostatic balance, the geostrophic balance, what happens when you now start throwing friction in, how does everything change. It's just sort of a good summary, I think, to put, if you guys don't remember or confused, you can go back and look at it. Sort of one thing, I guess, that I just want to mention again is, so all the forces, right, we talked about, but really this pressure gradient force, we break up into the vertical and to the horizontal because they react very differently sort of to the horizontal and the vertical, right? So our vertical, we said, was really balanced by gravity. And so because of that, sort of we had this balance, the hydrostatic balance, whereas in the horizontal, this is where sort of different stuff is happening. So really when we're talking about the pressure gradient force, it's really important that you break it up into a vertical component and to the horizontal component. Whereas the Coriolis, the friction, and everything else, those are just what they are. Does that make? I think that, yeah, so that's all I had for today. And if you guys have any questions, it's a lot of stuff, a lot of material, you can go over whatever, or if you just want to come ask me or whatever.